Hi guys, Ben again, and welcome back to another tutorial. This time we're going to be covering the basics and concepts. Think of these kind of like the rules of 3D printing. Okay, so the concepts are essentially, as I mentioned before, the rules of 3D printing. And this is what allows us to bring a 3D digital object from the digital plane and actually make it into something that's physical that you can pick up. And I want to preface this by saying that you don't need to have a perfect understanding of all of these concepts, but whenever the library staff says that we might need to do something like add supports or make it a higher level of infill, we will determine that for you. But basically, this is just to let you know what we're doing and then why we do these certain things. So the concepts can determine things such as the amount of time or how long it takes to print, how strong a print is or the durability, the material usage or how much that you'll be paying for it ultimately, and the ability to actually make it. Can it be made with or without some of these concepts? So let's look at a couple of these together. Okay, so probably the number one concept that we have, at least in FDM printing, which is the most common form of 3D printing, is the objects are built from the bottom to the top. So here you can see a time lapse of an object that's being made with different supports and brims at the bottom. But the number one rule that we have, at least in the most common form of 3D printing that we offer at the library, is that objects have to be built from the bottom to the top. One of the first kind of vocabularies that I want you guys to get familiar with is the concept of mesh. And mesh is kind of weird, so I want you to think of your favorite video game character or your favorite animated character from an animated movie or TV show. And it's kind of weird to think about this, but did you know that they're actually hollow inside? So if you've ever played a video game before and you get too close to a wall and you can kind of like poke your head through that solid wall because you find a weird area inside the mesh. Actually, all digital objects are hollow inside. And that's kind of weird to think about because our minds, we as humans, we think that they are, solid inside, but they're actually not. And that's something that we have to do in 3D printing is when we have an object, we have to put something inside of it. So that's one of the, I guess the second biggest concept that we have is adding different things to make this digital object that's hollow. It's just the skin of the object, and we have to put something inside of it. So if you look at this picture of this bunny rabbit, this is one where he's been cut in half, and as you can see, what that digital object is it's only the skin of that object. There is nothing inside of that digital object, and that's kind of weird to think about, but that's one of the number one things that changes. It is the number one thing that changes it from the digital realm into the physical realm that you can actually touch. So how do we do that? So one way that we do that is we design the 3D object in something called CAD, and that's where it's still inside of its mesh form, where it's only the skin. But we have a special software that we use to communicate with the 3D printer, and that is what we use to determine what goes inside of the print. You don't have to have a perfect understanding of this, but it is something I want you guys to, try to wrap your brains around, to kind of try to throw it around a little bit today. And the following slides after this are going to talk more about how we put stuff inside of the objects. And so just kind of think about that and think about how are we going to put stuff inside of this empty model to make it for something we can actually pick up and hold. Alrighty, so one of the concepts that's probably going to affect you all the most is probably going to be the idea of supports. So if you remember that time lapse that we looked at where it went from the bottom to the top, what happens when we have things that are overhanging? Let's look at some of these examples. So let's look at the Y, and that looks like that's okay. There's nothing underneath it because it's going up at a gradual angle. But what about that T? If you look at that T, it's a real sharp right angle. And as you can probably see by this Easter grass looking mess up on the bottom right, if we don't put something underneath an object and it's building from the bottom to the top and it has something called overhang where it's overhanging the bottom of the object, gravity's going to pull that down to the bottom of the build plate and you're going to get a mess. And it's something that we have to try to avoid. And one way that we do that is we add supports to an object. So the general rule that we use with adding supports or trying to not add supports is using a wide base and a narrow top. And that doesn't always mean that we have to build it, build it that way in CAD, but whenever we build it on the build plate, it has to be generally a wide base and a narrow top. Now we can add supports, but just know that those are things that you're probably going to have to take off as you go throughout the cleanup process. And you might be thinking like, how do I know whether I use supports or not? The general rule is if you are looking at it and it looks as though something is floating in space, odds are you're probably going to need to add a support to it in some way. There are websites when you find predetermined prints and ready to go prints like on Thingiverse. They will tell you whether or not, most of the time, if it's a good reputable print, whether or not it requires supports, or you can look in the comments section as well. But this is something that is kind of catches people off guard, especially when they want really elaborate prints like dragons and castles, or really kind of complex prints. Just know that you may have to add supports to this, which will then have to be removed after the 3D print is complete. Okay, here's a couple common examples that are real common prints and times when you would probably need supports. Let's look at the dog. So the dog, if you were to look at him, he's going to build from the bottom to the top. So the first layer that it's going to build on him is actually going to be his feet, and then it's going to go all the way up to his legs, his upper thigh, and then it's going to build his belly. But if you look underneath that, if we didn't have a support, there would be nothing underneath his belly, and his belly would actually just flop to the ground. Let's look right underneath that, the cats, the 3 different cats. The one on the left is one where there was no supports and there was nothing underneath him at all. And you can see his butt fell off, his belly's dragging, it's all stringy, and it doesn't look very good. The middle one, actually, we have the supports, and then on the right one, we've actually removed those supports. So that's kind of an example of those kind of like quadrupedal, the bipedal kind of humanoids. Those are the ones that kind of require them the most. If it's overhanging and there's nothing underneath it when it's building from the bottom to the top, we have to put something underneath it. Otherwise, we're going to get a mess, and it's not going to look very good. Other common examples are balls. Balls often, they sit on a really small surface area and they tend to rock, so we often put a support underneath that to kind of give it some more stability. Or look at the Star Wars character up here of Baby Yoda, the Mandalorian. He has a kind of a laser blaster, but it's way out at a right angle. If we were to build that without a support, it would look like it melted. It would just fall straight to the ground. And one last kind of note, we do have a special type of filament that we can run on our dual extruder. It's called PVA, and that is a water-soluble filament. So by request, we can actually put this filament on your 3D print, and you can put it in water. Depending on the size, it can be anywhere from a couple hours to a day, and it will actually dissolve the support, so you don't even have to pull them off. But that really is more for complex prints. A lot of these are, it's just easier just to pull them off, like on the cats and the dogs. Okay, so here's kind of a time lapse, and this is on an Ultimaker 2 Plus. This is actually one of the printers that the library owns. But kind of watch this as I talk and go through this. One thing about supports is you don't have to add those manually when you're designing an object in CAD. We have a special software that we use at the library, and what that does is it allows us to automatically generate supports. In those supports, we can actually tell it what type, how dense, how many, and we can't even use like support blockers if we don't want them in a certain spot. We can say, hey, don't put supports on the face, don't put supports over here, only put supports if it's touching the bottom or in a certain section. Those are ways that we can do that, but let's take a look at this object. This is looks like a car manifold that was designed on this, and what he's doing now, this is kind of an illustration of actually removing the supports. So those over there, those are those little fuzzies or something that kind of come on that. He's pulling it off with pliers, and we have a lot of these tools that you're more than welcome to borrow at the library. If you don't have them at home, you can borrow some of the needle nose pliers. He just pulled the brim off of that. They don't always snap off quite this cleanly. Sometimes you have to use things such as files or sandpaper to kind of make them look a little bit better. There's a hole there, so you can see sometimes to get a clean hole, you have to be able to put a support in there so that it doesn't collapse or kind of fall down. It's kind of a good illustrated example of how the post-cleanup process works with 3D printing. Okay, so progressing from supports, the thing that goes underneath a support or whatever, it goes like over a certain distance, we call that overhang. It's anything kind of like the name suggests, it's hanging over something. And there are certain degrees that we can get away with before we have to add a support to it. But if you have two objects, like for example the one in the bottom, you can see that that is kind of like a tube or like a tubular shape, and it's actually dragging the printer over top of it really fast. And we call that bridging, and kind of like a bridge in real life, it's the connecting of multiple parts together without using supports. Now this can be a little tricky to determine whether this can or cannot happen, and it's really hard to kind of illustrate it, but as you can see in the top right corner, if it's the longer the distance, the less likely it's able to complete that bridge, and it'll start to sag in the middle of that. Now alternatively, what this person could have done is they could have put a support in it, and what the support would have done is it would have made it to where they would have had to have taken it off off. It would have taken more time to create because the printer has to make those things, but it would have probably ensured that it wouldn't have drooped in the middle as well. So there's advantages and disadvantages to both, but if you are able to bridge something, it usually takes less time and it uses less material, so that's less that you have to pay for. Here you can see a couple of examples of bridging and overhang. So you can see this object was actually made in our Eiffel Tower. Was actually made without any type of support underneath there. And this is kind of like a really good concept for understanding how bridging works, because if you look in the areas that are circled, you can actually see like the very base of the Eiffel Tower. That was actually 4 different pieces that went together and it bridged at one singular point at the base. So there was no supports that were put on that, but it was at such a gradual angle that it was built up that it was actually able to make that bridge. And now let's look at, there's actually bridges all throughout this object. If you look at the top rail, the one with the biggest oval, that's a bridge on top. They did not put supports ever on that little handrail that was on there. Or look at the support structure as it goes at the very top circle. That one has different bridges that were made all throughout this. So this is just one giant overhang bridge 3D print. But let me show you, if I can show you a video of what this looks like. Alrighty, so here you can see this is a time lapse of what I was talking about, and as you see there's no supports on this, and what it's doing is it's such a gradual angle that it goes up at that it does not require supports as it builds through the time lapse. It's kind of weird to understand this, but just think of it as just getting right to the tip point before it falls down onto the build plate, but it building so gradually that it doesn't quite fall down. It kind of just sags just a tiny bit, and then it will build on top of that previous layer again, and again until it gets to the very top of it. But let's watch this time lapse. Here's one last example of a bridging happening inside of a 3D print. Again, another concept that does not require supports. And as you can see, all of the areas that I've circled in here, so her sword, her hip, her fingers, her armpit, those are all areas where they actually were conjoined into one singular bridge within an object. And it's kind of weird to think about again, but just think of this as multiple points that start at different points and they join together at one singular point. And it's so gradual the way that it builds up that it does not require something else underneath it to be built. And that's kind of what separates like really good models from the ones that are, I wouldn't say not so good, but the ones that are really impressive. It's the ones where you can just plug them in, print them, and then they come out without any type of cleanup at all. And those are really the most interesting marvels when those work out. So if you remember back at the beginning of this presentation, I said that all 3D objects are actually hollow inside. So in order to actually make these things come to life, we have to put something inside of it. And the term we use for that is called infill. And infill is basically, as the name suggests, what we put inside of the object. And so as you can see in this picture, there's different types of infill that we can do. We can actually change the pattern and we can change how much is actually in there. So if you look at the very bottom right, that is 0%, that would be 0 infill, and it slowly gradually goes up in increments of 5 to 10 all the way until it's 100% infilled. And you might be asking yourself, well, how do I know how much infill to use? So basically the infill is determined by the use of your object and what you're going to be using it for. If it's something that's just going to sit on your desk, it's not going to be touched very much. It's not going to really be handled or thrown around the room or anything like that. You can just use a small amount, like 15%. That is enough for it to become a solid object, that it's not going to cost a lot, and you can actually get prints to be a lot less expensive by actually making them mostly hollow inside. So that's more for like desk sitters or organizers or something that's not going to be touched very much. If you have something that's going to require light handling, it's something that's going to be touched a little bit, but it's probably not going to see any type of real abuse or any heavy use at all, you might want to consider something between like 15 and 20%. And then if you had something that was going to be used outdoors, it was going to be like a real, heavy play thing that you're going to use, you would want to have more infill percentage with that, so something around 40%. But what we found out is actually after around 40%, we start to have diminishing returns where there's not much difference between 40 and 50 and 60%. There's just not a lot of return on the strength or really the usage of an object at that point in time. As the infill increases, it's also going to increase the print time, and it can actually get quite significantly longer because that's more that has to fill inside the object. It also increases how much you're using, but the durability also increases significantly. Alright, so we have three different examples here. So the one on the left is one where you're going to use a very minimal amount of infill. And then I actually suspect this probably has almost no infill inside of it. That's actually it looks like a lithophane version of the moon. And I bet you he put a light or an LED or something in there. And if we put it in with infill, well, it would block the light. It wouldn't be able to illuminate it. So I bet you that's mostly hollow inside, and that's how he's able to actually get the moon to actually light up like it's a nightlight or a little bulb inside of it. Let's look at the middle object here. This one looks like looks like a bust or a statue of some type. This looks like something that's not going to probably be touched a lot. So you could probably use like a medium amount of infill. You'd probably want to use like, I don't know, around 20% or so, and that would make it to where it's strong enough where you could pick it up and move it when you needed to. But you really want to fill it all the way in because it would use a lot of filament to fill it all the way in. The one on the right, that's something that looks like it's actually going to be used more with some heavy outdoor use. Looks like it has a rope that's around it. Those are ones that what we would want to do is you'd want to fill that in because we would need it to have a lot of strength, especially if it's going to be holding a lot of weight or be using it to pull logs or whatnot. That's one where you'd want to put a lot of different infill inside of it. Our next concept that we have is something called layer height. And layer height is kind of an odd one too to kind of understand, but the best way that I can describe it to you is by resolution. So if you've ever opened up a YouTube video or you've tried to play something and it's real fuzzy and it doesn't really look very good, that's called low resolution on that. So think of layer height kind of like your resolution or how clear an object is when we go to make it. So a low layer height is one that has lower layers on it. So the one on the left, if you look at the image on the right, it has 0.05 millimeters. That is a low layer height. It's very smooth and the lines are very, very small. So each line that is on that object is 0.05 millimeters tall. Now look at the one on the right. The one on the right is 0.4 millimeters tall, and it's significantly taller than the one that's on the left. And what this does is if you have lower lines, it makes it much smoother and it's actually much stronger because you have less area that it can actually delaminate and come apart. Now, if you have higher layer heights, this is actually good for prototyping, rough drafting. So if you made something and you weren't quite sure whether or not it was going to fit or not, you could actually just put it on the 3D printer and set it to a high layer height because that actually comes out significantly faster. But let's talk about that a little bit. Okay, so here we have some layer height cubes, and this is a good illustration of actually how layer height looks as it goes throughout its process. So on the very left we have 0.8 millimeters, and it goes down to 0.6 to 0.45 to 0.3 to 0.1, and you can see what we found is kind of the good mixture, what I would consider the best bang for buck in terms of time and actually quality coming out is around 0.15. So anything that starts to get above 0.2, you really start to see the lines that become much more dramatic and you can see them. But whenever you want your final product and you're like, this is the one I want, anywhere between 0.1 and 0.15, that's considered a good fine quality when it comes out. And the biggest impact that we actually have of layer height is how long it actually takes to do something. So the one on the left is a little extreme, and most people wouldn't actually want something like that, but it's just used for illustration purposes. This is a vase, 4 different vases, and the one on the left actually only took 8 minutes to make. And look how sloppy that looks, but it only took 8 minutes to make. But the one that's in the middle left, the one right next to it, that one actually took 15 minutes, so almost twice as much time. But you can see as the time goes up, your layer height also goes down. So as you continue to go up, for example, the one after that, that one took 30 minutes to make, but it's actually exponential. So it gets more and more and more as your layer height actually decreases. So the one on the far right, which is 0.08 millimeters of layer height, which is extremely fine, that took 2 hours to make that same object. So I hope that you can see that whenever you want your final product and you've gone through all the bugs, you've got all the bad things out of it, you've modeled it, and you know that it fits, you'd want to use a nice layer height like the one on the far right, and then that one would look really good when it comes out. But if you're not quite sure if this is going to fit or not, and you want to kind of just practice, you might want one that's kind of closer to maybe the 30-minute one or the 15-minute one, just to see if it works before you use all of your time up. One last thing about layer height is whenever we actually put our layers down, it's important that we try to position our object, because remember we build from the bottom to the top. We want our layers, if possible, especially if it's going to be used with something that's going to have a lot of strain or hard use with it, we want the lines to be perpendicular, which means that it needs to come to a right angle as to how it's going to be pulled. So if you look at the one that's actually holding that bag up, the teal colored, turquoise colored 3D print, the lines in that one, if you look in the bottom right, are actually going perpendicular to how it's being pulled. But if you look at the silver example that's on top, those lines are parallel to the object in the way it's being pulled. And what this means is that it's more likely to actually break or delaminate because you're pulling with the grain, not against the grain. And this is something that we can kind of determine whenever we put the object onto the 3D printer. We might have to turn the object on its side in order to make sure that our grain structure actually has the highest strength tensile instead of having it pull with the grain. Okay, one other concept that we kind of need to discuss is the concept of shell. And another name that this has been given is the parameter of the print. So if you remember when we looked back at that bunny, how it was just the skin of an object, think of shell just as the thickness of the skin. So there's no infill in this at all. So if you look at the right-hand object, those are the different shells, or how many times it will actually go around the object before it begins to do its infill. So all of those have zero infill. There's no infill in those at all. It's only shell that's in those. So it's only doing the outside of the object. And you might be asking, well, why do I need to have a high amount of shell? And really it depends on what you're going to do it with. If you were going to use just an inside object, you might only need 2 or 3 shell, especially if it's not going to see any type of heavy use at all. But shell can also determine things such as how watertight something is. If you want something to have a high impact strength, for example, if it's going to hit something hard or if you didn't want it to drop, you might want to consider putting something like 4 or 5 shell inside of it. It strengthens weak points as well. So if there was a stress point or a point that had a very small amount of surface area, if you increase the shell, what that does is it makes it much stronger around that area because you have more outside layers of your object. And this has no outcome on the infill. Just know that the infill is completely different than the shell. Here's a couple examples of them. So if you ever had something that you were going to use in the water, we really highly suggest that you increase your shell count on that. And again, this is all of these concepts that we've talked about so far are things that you do not do while you're modeling an object in CAD. This is after you bring your object into the library, and that's where we can determine and tell that object how thick to be on the skin or the infill or whatnot. So if it's going to see water at all, it's highly, highly recommended that you increase the shell, which is the outside skin of the object. As you've seen, a lot of the infill is actually honeycombed, and we don't want to get water inside of that. That's whenever you start to get things like mildew and mold, and that's when you get nasties and bad stuff. If you have threads, for example, the bolt and then the tap that's on the left, those threads, if you want to really increase your shell count on those, because if you have an increased shell count, it's much less likely to wear down, and you really don't want this stuff breaking at any point. Or let's look at the middle object there. The points that I have circled on those are actually the weakest points of the object. And if you were to take that thing and just slam it down, that's most likely where it would break. It's because it's the thinnest, weakest point of the object. So one way that we can strengthen that is we can actually increase our shell, which will increase the thickness of our skin so it's much less likely to break in that area. Alright, so this is one that you can probably find on a site like Thingiverse or another community site that hosts different files that you can download. It's the print in place. And these are really amazing to see because what happens is it actually builds these without having to be assembled. So if you look at that FlexRex, that's what we call the FlexiRexy, that one in the bottom right, it's actually built with hinges inside of it. So it builds the hinge around the gap and it actually moves after that. So we don't actually like snap these together or anything like that. We typically don't teach how to make these at the library because it's pretty complicated unless you're using like a preset linkage or a preset model that you're putting them together with. But what we do is we call these articulation models because they move to some degree. And what happens with these is they have different gap tolerances, and it has a small enough gap tolerance to where it can build it where it won't be fused together, but it's spaced out enough to where it can actually freely move, and it's really cool to actually see these things move. Again, if you wanted to see one of these or kind of play with one, I would go to somewhere like Thingiverse and I would look for moving prints, or they call them articulation prints. There's quite a few, especially if you filter by the top results. I'm sure you'll find quite a few that are up at the very top. Okay, here's a couple cool examples. On the left, you can see this is an articulating fish, and this actually requires no supports at all whenever you make this object. All you have to do is put it into the 3D printer and put the right amount of shell and infill, press print, and it should come out. It might require a little bit of flexing and kind of maneuvering to kind of make the parts move smoothly, but this is, again, there's tons of these types of articulation prints and Thingiverse that you can bring into us. The one on the right, this is called the iris box, and this is one where you can, use it as a little jewelry box or whatever little knickknack you want to put in there. Again, a print and place model. All you have to do is pull it off, and it might take a little bit of kind of meandering and kind of using it a lot to kind of make it nice and fluid and smooth. But again, another print and place model that requires no supports or assembly. Okay, so assembly prints are kind of the last kind of cool concept that we have. These are ones that are actually built in small pieces, and they're slowly assembled piece by piece by piece until you get a larger whole piece. Most of the concepts that we talked about so far have been singular objects that we've made, and they've kind of revolved around one object that prints at one time. But you can actually print multiple pieces, and those pieces can later be put together into a larger whole. And we call these assembly prints. Sometimes these have snap together parts. Other times you're going to have to use things like glue to put them together, or they might even require other auxiliary parts such as nuts and bolts to make them work. I actually created a Stegosaurus that was 96 pieces, and I built him piece by piece by piece by piece by piece until I got him into one large 2-foot long actual dinosaur sculpture. And it's really cool to see, so stop at the library sometime to see it. Other qualities of assembly prints is that they're usually high functioning compared to singular prints. They take more time, and they sometimes take a lot of patience to assemble. What you'll find is that sometimes the tolerances in your 3D printer do not align up to the same ones that someone may have put on Thingiverse. That might require you having to make different modifications or kind of whittling the pieces down a little bit to kind of make them work. Multiple pieces means you have a higher rate of failure, or you might have a broken part, so you might have to go back and reprint that part again. And it also allows for parts to be printed with supports and other parts not with supports. So if there's one object that's bad, instead of putting supports on everything on your build plate, you can just single out those single objects that need help and put them by themselves. And it's also a way that you can exceed your build plate capacity. So we have around a 200 by 200 millimeter build plate, and this is a way that we can actually build more than that. It's a way that we can see beyond the constraints of the size of the printer. So that's basically what assembly prints are in a nutshell. Here's two kind of common examples. So I did a Stegosaurus before, but I've also done this T-Rex before as well. You can see on the T-Rex, I think he's around 50 or so pieces that once he's put together. But you can see he was built piece by piece by piece until he was assembled into one larger actual dinosaur. Or the one on the left, that's actually a ukulele, and that's actually built in 4 different pieces. So you can see it was built in 4 different pieces that were put together, but they used auxiliary parts. So they used ukulele strings and the tuning keys that were at the top. Those are actually bought and they were put into the object. So this is one where it's combining different real-world objects, meeting into the 3D object to make the actual functioning assembled print. Okay, so what we're going to do soon is we're actually going to jump into TinkerCAD, and I'm going to show you a real basic model that we're going to create that actually kind of exemplifies a lot of the concepts that we talked about today. So TinkerCAD is one of the coolest, best, real elementary CAD softwares you can use. It's cloud-based, it's free. Check it out because that's where we're going to head to next. Thingiverse, I mentioned this multiple times in the video. This is a Creative Commons that you can go visit, and you can download pre-made designs such as the print in place or any of the other cool ones that we saw today, like the Eiffel Tower, and you can bring those things into the library on a USB drive, and we can try to make them for you. Your library card, it also comes with a LinkedIn Learning course. This is something that you can use for self-guided courses, and it can do things other than 3D printing, all kinds of different course topics. I think there's like over 1,000 different types of content that you can view on there. It's really cool. Check it out. It comes with your library card. And lastly, YouTube. One of the coolest areas that I've gone to kind of see what is going on in the world of 3D printing is on YouTube. It's a good way to learn tutorials, but not only that, but just to see what other people are doing and to kind of stay on top of it. So let's jump into TinkerCAD. Let's go ahead and we're going to try to make a fidget toy, and I dubbed this fidget toy the Impossi-ball. So let's see if we can make that together, and we'll talk about it and how it actually works. What we're going to do is we're actually going to try to make this object here, and this is the Impossi-ball here. And basically what the Impossi-ball is, it is a cube that's been hollowed out, and you have a trapped ball that's inside, so it will rattle around, and you shouldn't be able to get the ball out of there without breaking it. So the cool thing about this is it actually exemplifies a lot of the concepts that we talked about today, such as bridging at the top, or building a support underneath the ball. So what we're going to do is we're going to jump into TinkerCAD, and we're going to see if we can make this. What I'm going to do is I'm going to go to TinkerCAD.com and we're going to begin modeling the Impossi-ball. Here you can see I'm on the main page. On the left-hand side, if you press Designs, there's going to be a button on the right that says New, and this is what we're going to use to click to design our Impossi-ball. So click 3D Design New. And from here, it's going to give us a randomly generated name. Here is Grand Lilo Curicon. We don't want that. So let's go ahead and we'll rename it Impossi-ball and press Enter. And that is the name of our creation. We're going to begin by dragging a cube onto the screen. So here is our cube. And what we need to do is if you hold down Shift, we're going to drag this out and it's going to do a uniform scale. And we're going to go all the way up to 60. So 60. Perfect. Alternatively, you could go through and you could click and you could type in 60 into each one of these values. But if you hold down Shift as you move, it'll actually save you some time. The next thing we need to do is, this is our housing, when we need to make a ball that's going to create a cavity that will fit inside of the Impossi-ball. So go ahead and click Hole here after you drag on your sphere. And again, left click, hold down Shift, and we're going to drag down to 70, so 70. And then let go. Perfect. Alrighty, so this ball needs to fit in the middle of this. So what I'm going to do is I'm going to drag it over and get it kind of situated. If you hold down your left mouse button, you can create a selection radius. So I'm going to select this. You can alternatively press Control and A, and that will highlight everything in the build plate. Up here on the right, there's a button that says Align, or you can press L on your keyboard. And we need to do a 3-point alignment so that we can get this into perfectly centered. So 1, this one already was aligned, 2, 3. And it's always the middle option on each one of these. And as you can see, our ball is perfectly centered inside of here. I'm going to highlight everything again, or you can press Control and A. And I'm going to press Group or Control and G. And what this will do is it's going to create a cavity inside of our housing. But what you'll notice is our housing is actually up in the air. And if you remember, when things are up in the air, we need to do something that allows us to not have to generate a support, because if it's up in the air, it's going to make a mess. Go ahead and click on your object and press D on your keyboard. And what this will do is it will drop your object to the bottom of the build plate so that we know that we're down. Good deal. So we have our housing, but now we need to get our Impossi-ball. So go ahead and drag another sphere in, hold down Shift, and we're going to drag this one out to 45. Perfect. Now go ahead and grab your ball and drag it inside. And what you want to do is make sure that it's big enough that it's not going to fall out of the housing. And you can see it is. The ball is bigger than the holes here. But what we need to do now is we need to make sure that this is actually inside of, it's off of it a little bit, off of it. So let's make sure that we're aligned. Go ahead and highlight everything. Press L or Align. And we're going to do the same thing, 3-point alignment. 1, 2, 3. And if you can't kind of get it to align, you can always pan your camera to get it to give you different options. So left click off. And you can see now the Impossi-ball has been made. So what's cool about this object is that it's going to exemplify bridging. So bridging is done here at the top on the circle. We'll also have to put a support underneath, because you can see our ball is up in the air. But this support will actually be removable. So as soon as you snap off the support on the bottom, what it will do is it will trap the ball inside. So the ball will be kind of rattling around inside of its housing. There's one last thing we need to do, is we need to group everything together and export it as an STL. So go ahead and highlight with the selection tool, press Group or Control and G, and this will create one singular object. And from here, there's a button that says Export, Export as STL, and this down here is what you're going to put on a USB drive to bring to the library. So this is actually what it looks like on the librarian side. So this is what we do after you give us the STL, but I kind of wanted to show you all like how we put on these different things and how we can kind of determine these concepts. So you wouldn't have access to this, but it is kind of cool to see how we put the supports on and things whatnot. So I'm going to hit Upload New. I'm going to choose my file, and it's in my downloads. I'm going to put the Impossi-ball in. I'm going to save and go to my files. From here, I'm going to do something called layout. What layout does is it allows me to see this right here is our three-dimensional object. This is the one that we just modeled. And this kind of rectangular shape, that's actually the bed plate. That's actually where we build on the printer. So what I'm going to do is I'm going to go over to hit slice. And from here, what I'm going to do is I'm going to tell it what we want for those parameters. So I'm going to tell it, where do you want supports? I only want it for things that are touching the build plate. So the ball is what I want it to be on there. This is where we can determine our layer height. So we talked before that it said 1.5 is a good medium. This is also where we can determine our infill. So we're going to play with this one a little bit. So maybe something like 25 or 30, but we'll be on the safe side and say 30. And this is where we can do other parameters such as how fast we print, or up here we can determine how hot it is. Don't worry about that. The big ones we want are our infill and our support. So I'm going to go ahead and press slice. And it's going to begin generating it, and it will give us a preview over here. So if we press preview, you can see the area in pink here is our support. So this removable support will come off, and it's actually going to be able to bridge this hole here. So it's really cool. So it's actually going to be able to create this without creating a support on the side. But as soon as this pink support is snapped off of there, when you manually pull that off, you will have the ball trapped inside. I want to thank you for watching this tutorial today, and I hope you had a good time. If you have any questions, feel free to contact the Lebanon Public Library Tech Center and ask for Ben. For all future events, be sure to check out our website and event calendar at lebanonlibrary.org. Thank you, and see you soon.